So, welcome. My name is Jiří Bajer. I work for Rosum as a software developer and Python architect. And today I would like to talk about splitting the code of services that are used for serving machine learning models into part related to infrastructure that can be provided and operated by the platform engineers, and to part which is closely related to the machine learning algorithms itself and the domain code, which will be handled by the researchers. So this is all about a situation where the startups in the very early phases don't have time and resources for clean code, architecture, or whatever. So they don't invest much into proper software engineering. And when successful, they will quickly end up with production code that still has features of MVP. Usually, the things that I observe in those situations is that a mix of infrastructure and machine learning algorithms. That means that the researchers that originally created the code have to care about both, not only about the algorithms, but in order to keep the service alive, they have to mess with the infrastructure, which is actually not their job, and they are wasting time on that. Also, the code usually is split into more microservices, and they contain copied of code that should do the same thing, but often does it a little bit differently. And last but not least, once the system grows up beyond some level, the use cases, what the code should do, are usually buried really deep in the domain logic, and it's hard to understand, hard to onboard. And in this situation, usually the tests that are available are integration tests because of the infrastructure mixed with the algorithms, and it's a pain to grow this code and evolve. So what should be done with that is to really split the infrastructure and domain logic. The boilerplate, the code that provides cloud-native features, startup, shutdown, probes for Kubernetes in order to observe the lifecycle of the services, it should be unified across the services. And the infrastructure itself should be encapsulated and injected into the services, and the researchers should care only about the parameterization of the infrastructure, not about its actual code. And basically, also to highlight the use cases provided by the services, the decisions, the if statements and try except statements should be pushed down to lower level of detail hidden in the domain logic. So when I started thinking about how to fix the situation, I end up thinking, okay, so what kind of services do we actually have? What do they have in common? And where is the boundary between the domain logic and the infrastructure? And, oh, wrong button, sorry. I ended up learning that our domain and our use case leverages CPU-bound prediction services. So they usually run in a single process in a container, typically in Kubernetes. They don't need to have multi-threading or async I/O because of the CPU-bound nature. They run in infinite loop, where until there is a signal to cleanly shut down the service from the Kubernetes environment. And they basically do that. They poll for some I/O source, for a message, for some input data. And this I/O source is usually a message broker, like RabbitMQ, like Kafka, like Pulsar, you name it. Or it could be a web service, so incoming HTTP requests transformed, the request is transformed in a sort of message. It can be represented by a simple Python data class, and they process the message, which usually means based on the type of the message, you pick the right callback and let it process the message. And then the callback itself needs to access not only the machine learning code, but also some infrastructure. I will show the details later, but this realization led me to encapsulate all those infrastructure clients into code that, again, is sort of black box for the researchers, that is just called for methods like send a request over HTTP or push a message into message broker that doesn't require too much thinking about the underlying technology. And then at the end, they either acknowledge the message consumed from the broker or send a HTTP response. So all this is related to the actor model with a single process, potentially leveraging multiple cores, because the machine learning algorithm runs in C land, so it's able to leverage all available RAM, all available cores in the C extension code. But it could be also applied to asynchronous code. We didn't do it yet, but we plan to do so. One more thing about the architecture, this style of distributed system design uses no in-memory state. All state is persisted in some persistent storage like databases or object storage, and there's no cross-service shared state. So when I looked at our services, I realized that most of them are messaging services, the consumers from a message broker, and they are actually very, very simple when we look at them. This is the infinite loop until there is shutdown request, like signal from Kubernetes. They just poll the topic with some timeout if the queue is empty on some queue consumer, and they get message payload and some metadata, like who is the sender, what is the timestamp, distributed tracing correlation ID, etc. They deserialize this payload and metadata into one of the available data classes, messages, and they get an instance of this message. And if the topic wasn't empty, they just process the message, run the right callback depending on the type of the message, and acknowledge to the broker that the message was actually consumed. It's so that simple when it comes to the messaging service. And usually there are not many frameworks for that. This is usually homegrown code, but it has really repeating patterns like that. Everything else is just an implementation detail. And as you can see, it doesn't matter if the message came from Kafka, RabbitMQ, Pulsar, or whatever, or if it was provided as an instance of this data class just in memory and calling this loop or injected into this loop. And there is no I/O except the polling of the topic here. Especially here, there is no I/O hidden, like for consuming the message. There can be I/O for sending outgoing requests, as we can see later on. Let's assume that the messages are just JSON to be simple to imagine. But again, it's not related to the particular serialization format. So when we compare it with another type of services that we have, the web service, again, we have infinite loop until the shutdown request. We are again polling for some message, perhaps with some timeout, this time from HTTP server, and we can again get payload and HTTP headers. We can convert them to metadata to keep the same language as before with the message consumer. We deserialize again the message from payload and metadata. And if we consume something, we again process it. And this time we get a response. Then we just send the response back to the sender as we are synchronous web service. So it's very similar beyond the headers versus metadata. And again, you can imagine that you have gUnicorn with something like Flask running in pre-fork mode, just implementing something like this. So if we put those two approaches, the message consumer and the HTTP server-based service, side by side, we can clearly see that there are some differences, like how do we consume versus poll for HTTP request. There's some additional conversion. There's automatic acknowledge versus sending response. There is no response in the asynchronous message consumer style, but they are pretty similar. There's something in common, and especially if we would manage to this little bit of code, the process message, this would be the major place where the researchers put their domain-specific code. They would be completely isolated from the way how their message handlers are served. If they are synchronous, if they are asynchronous, if they are jobs, like Kubernetes cron jobs or one-time jobs, it really doesn't matter. It could be a batch job that doesn't have this infinite loop, but while the batch still contains some messages, but again, just calling the same mechanism. And when I realized this, I started thinking how to isolate the researchers also from the infrastructure that necessarily needs to be used inside the message handler. So imagine a concrete service using this approach. This is an example of a really trivial message, a data class that has some type, some string describing what kind of message is it. So we can put this string into the metadata or HTTP headers, and it has some payload that is part of the, let's say, JSON body. And then we have some service. Imagine your microservice running in Docker container in Kubernetes. In this case, this is a message consumer. And this service has message handlers for each type of this data class. You have some callback, some method on the class. Then we have some fancy predictor, our deep learning code, whatever. We have some wrapper over the persistence layer, and that's it. If you look at this message and this messaging service, those parent classes are completely domain agnostic. They don't contain any knowledge about the use cases, about what is the purpose of our services, while everything else in the child class and in this concrete service is really domain specific. The amount of boilerplate is minimal. The repeating bits are basically hidden in the base classes. So let's continue with the body of this example of microservice. We definitely need to make some outgoing I/O. I put there a lot of possible clients to demonstrate how would it work beyond just database. So let's imagine that we are pushing some messages to Kafka. We have some producer for that. Thanks. So we will definitely need to make some outgoing HTTP calls, synchronous blocking to some other service to get some additional data. We definitely need to collect some metrics and expose them to Prometheus for scraping, and we need to register the metrics themselves. And we will have some database persistence using SQL Alchemy. So this way, in the domain-specific service, we say that we have this infrastructure footprint. We need those clients for outgoing I/O. With this messaging service, we are saying this is our footprint when it comes to incoming I/O, where we collected the messages. This is what we need to send from this message to the outside. Those infrastructure clients are registered, like you can see, and they actually, when they are started, when the service is started, they all are started. They perform connectivity checks of the remote counterparts, and they react to graceful shutdown of the whole service as well. Imagine that the metrics are exposed in a child thread for you just invisibly on the background. So let's look closer at an example of the message handler, the thing that we registered for a particular data class for the message. So if we receive our simple data class, just do the prediction, we have the callback, and this is an example how to make the outgoing calls to I/O. So, for example, we load some data from S3, from some bucket. Based on the data inside the message, we will make some outgoing call over HTTP to some URL taken from configuration. We are measuring the elapsed time of this code for a separate Prometheus metric. And we are calling our fancy deep learning model its predict endpoint with the data we got from S3 and from HTTP, and then we process the result into relation database. Then we push a notification over Kafka about the result. So this is a trivial example of the top-level use case, and it clearly shows what's going on. I don't have to explain what the predict does. There are some implementation details, of course, but they are managed by the researchers. This code could be written by researchers or by the platform engineers. It doesn't matter too much. And it's understandable for both. And really, the amount of repeating boilerplate is minimal. I just say what I need to use and how do I parameterize the outgoing I/O, and that's it. So this is the top-level use case. And if you notice, there are no if statements, no try except. The cyclomatic complexity of this is just one. It is making outgoing calls, so it needs to be integration tested, but it needs just one test case. Everything that is sophisticated is hidden inside this predict call of our predictor, and it can be unit tested. So this is an example of how can it look like from the researcher perspective when just using the framework. Now imagine that there's a lot of going on the background. For example, when making this HTTP call, definitely there will be retries and give up and some exception handling, and the service needs to somehow cope with that. Will it crash and restart, or will it just log an error? What did it try to do and continue with the next request? You don't have to care, because it can be hidden in the parent class of the service, and you don't have to re-implement this logic whenever you use the client. So basically, those clients are wrappers that hide this complexity from the users, from the researchers. The same about connectivity checks, transaction rollbacks, and schema migration upon the service start. All this can be hidden, and you don't have to care that much when writing the use cases. Just notice that the registration of metrics and their actual measuring is a domain-specific concern. And also, the transaction boundaries are a domain concern. So they should be somehow visible from this code, shouldn't be hidden in some generic infrastructure. So basically, it was sort of hexagonal architecture ports and adapters, where all the incoming I/O and outgoing I/O is encapsulated by our wrappers, and we focus on the domain logic. We have an example. I mentioned the data access object for the relational database. This is an example how to wrap the domain-specific operations with a database. So again, we have some database client. We define tables, and we have some mechanism, some context manager for connections where we can execute some SQL statements, so no-brainer. Why is it useful to use data access objects, in particular for machine learning services? Because usually we have very, very simple domain, like not many entities, but many rows. Like we are processing a lot of, let's say, embeddings, and the embedding has few attributes, but we have really a lot of them. So wrapping, so the number of operations are usually crude, and some calculation that is delegated to the predictor that we saw before. So it's very beneficial to forget about ORMs and all the complexity hidden with them, and have really wrap all the database access in such simple class, so you know that you are making an I/O, you are working with an infrastructure. And again, this can be prepared by the platform engineers because the operations are not too complicated. And then the code really just calls safe prediction with the results. This is what the researchers are concerned about. And I already mentioned that there is some hidden infrastructure in the service. So basically, what do we need to care about, but not bother the researchers? The lifecycle management of the whole service and the individual clients, they basically have to start, they have to stop, they have to be configured somehow. We need to expose liveness and readiness endpoints. We need to work with distributed tracing IDs, and all this can be hidden in the base classes. Like the liveness readiness endpoints could be exposed by a background thread, and the liveness is just HTTP 200 returning without any conditions. The readiness will just ask all the clients if they are okay and report, yes, we are ready, as long as something I haven't mentioned, the before ready hook. When the service is starting, we often need to perform some expensive operations like doing database migrations or to initialize, to load some machine learning model. It can be huge and it can take some time to initialize it. So we need to indicate to Kubernetes that we are alive but not ready yet. So the readiness endpoint can cooperate with the service on making sure that this hook is already finished. And the distributed tracing is as simple as hiding the ID of a request that is passed from service to another to metadata / HTTP headers, and automatically copying it from the request to all outgoing requests that we make via the clients. The configuration, again, can be done typically from config maps and environment variables with some type coercion because the variables are strings. So this can be, again, done automatically by the service and exposing only the configuration items that were already taken from the environment. Also, the logging of the lifecycle of the whole service can be done automatically because the domain-specific code doesn't change anything on how the service is starting. Also, we can log every processed message. Just imagine that the data class has a custom wrapper that describes what's inside in a concise way. So you can, again, uniformly log all processed messages, just taking a look at their data classes. You can take all the domain-specific things from there. And again, the concrete domain-specific service doesn't have to deal with that. The metrics, we already covered the central registration. This is domain-specific. The exposition, again, in a background thread together with the liveness readiness probes. You can automatically measure the response time for each request. Again, you have the main loop, the infinite loop, so you can measure how much time did you spend inside. And you just have to care specifically with the web services that they need to multiprocess aware metrics. And a nice thing is that you can create IPython CLI where you can allow people to instantiate this domain-specific service. You can start it, let it connect to infrastructure, and it can be even a mixture of local dummy infrastructure and real remote infrastructure, perhaps in read-only mode. And then you can create an instance of the data class and feed it into the callbacks, into the message handler, and it will provide exactly the same thing that a production service, just triggered by you, not by a remote call. This way you can debug why is it returning something wrong. You put imagine that you connect to a running container, you're running bash over there, you run this IPython CLI locally inside the container, you have all the environments variable already configured, so you know how to contact the infrastructure, and you can instantiate a handful of classes, your service, your message, feed it, start the service, feed it into the handler, and you can put breakpoint somewhere, and really you have very luxurious debugging as long as you connect inside the container. You can do the same locally, of course. So, where's the domain boundary? We already covered the domain-specific code, and it lies in the concrete message data classes, like the prediction request we saw before. Then it's located in the concrete services like our predictor service, especially in its message handlers. They are the top-level use cases. And then the registration and use of infrastructure clients. This is our infrastructure footprint. And on the opposite side, the domain-agnostic boilerplate, the repeating code that is always the same, is hidden in the base classes, in the service, messaging or web service, parent classes, and in the message and its deserialization. It's always the same. And also the logic for selection of message handler and actually calling it. We have just a dictionary of registered pairs of message and handler, and just a dictionary lookup, and the infrastructure clients. Again, all with the retries and give ups, etc. So this is the promised division line where to implement the code once by platform engineers and what really needs to be implemented and tailored to every domain-specific service. And I have only a little bit of time for mentioning the framework wrestling, but actually I have some backup slides that detail all this that's listed on this one. So feel free to look it up on GitHub, where the whole presentation is published, including the speaker notes. But briefly, if I want to integrate some WSGI server or HTTP service with this approach, with this framework, I can use WSGI server and threading mixin from the standard library. It already has a facility for the shutdown hook, just plug into it. Beware, it has request size limit. You cannot put longer requests than 64 kilobytes. So it's sort of limiting, but if you put all the big data into S3 and have small messages that just refer to those big data, how to find them in the object storage, that's fine. And for HTTP request parsing and response generation and working with rising exceptions based on HTTP response codes, Werkzeug is pretty fine. Actually, you don't need Flask, you don't need Fast API or any framework like that because we are duplicating its functionality. If we decide to use Gunicorn, let me tell you a secret. Gunicorn is not only a tool that you have to run from command line and configure by a Python module, but it's actually a library as well. So you can import the Gunicorn application, you can call it, like tell it really start up, spin up that, you can configure it with your desired number of child processes, and it has hooks. So you can react to things like a new child is spinned up, so I will register its Prometheus metrics, it's being spinned down or killed, so I will deregister it, etc. And the multiprocess metrics, Prometheus, it means that we have to somehow collect the metrics from multiple child processes of Gunicorn. But not a big issue, and it's quite doable. The Prometheus client I already mentioned, it's ideal to run it via HTTP server in a child thread. If you borrow some bits from its exposition, it's pretty straightforward. It's actually text format, the response containing the metrics, and a thin wrapper on top of that will do the trick. And the details are in the helper slides. Alembic for database migrations on top of SQL Alchemy. Again, we know it, that it needs to be used from command line, but actually you can import it and call it from your before ready hook. So it's again quite doable. When it comes to gRPC, this is completely different beast. It is doable, but I doubt that anyone wants to go through the pain because it's so opinionated about the way how it's being run, like on-thread pool. It uses generated code, Python code, by a compiler from the stub. And you have to basically re-implement your stub and service, the server and client code. So I would be very careful when tasked by integrating gRPC into this framework. So that was all. It's not aimed as providing you a ready-to-use library, rather as an approach. Where is the boundary? How to think about this separation, and potentially how to borrow some things for your particular use case. So that's all from me. Thank you. And there's some reading list for you that inspired me when thinking about all this. Do we have time for Q&A?
Thank you, Jirka. Give him a warm thank you. I think if you need to run, but let's do quickly the top questions at least. And I will share the links to the slides, to Discord and my Twitter. So if you didn't catch the picture, it's all right. There is a question which is anonymous. Thank you for the talk. Are researchers ever talking to you about more requirements for infrastructure?
Not that much, because usually really the platform team covers this part. They observe some effects of improperly handled infrastructure, because usually we cannot cover all the edge cases when wrapping the clients. But usually they are pretty isolated, so not really.
Maybe you need to talk to them more.
Sorry?
Maybe we need to talk to each other more, like all together.
But I'm not worried about really bothering the researchers by the details of the infrastructure. They focus on the use cases, on the machine learning part, and it works amazingly well. And actually, I haven't mentioned it, but we can swap the type of the service, as they are very similar. Imagine that you originally started with a web service and then you swap it to a message consumer during some redesign of your distributed architecture. And it can be done without the researchers, because their domain part is exactly the same. Just change the wrapper, change the base class. That's it. So really rarely.
That's great. There is a follow-up question from Vojta. This was inspirational. Do you see a similar approach, i.e. splitting the infra and domain-specific operations in other companies?
And is it about me using it, or if I saw different implementations of...
If you see similar approach in other companies.
Yeah. In this approach, I applied it in 3 companies in a row. So I have some feeling that it's general enough to be applied to a reasonable niche in the machine learning projects. But as you have heard talks about different approaches, really not all projects are the same. We are CPO bound, and we really don't leverage Python threading / async IO. It doesn't help us. If we were processing a fast click stream with really short response times, with need for low latency, this would probably not be enough, and we wouldn't rely on asynchronous messaging and all this deserialization. It would lead to a different architecture. So I'm not claiming this is a panacea or silver bullet at all, but there are universal, interesting ideas behind that, or things that I realized. So feel free to borrow them. And sometimes you might be tempted to use a ready tool like the serving that Maciej was talking about a few hours ago. And sometimes it's really better to use a ready-made tool. Sometimes not. So if you decide that writing your own microservices is the right thing, I hope you can draw inspiration from this.
Okay, last question from Jan. Do you think this approach is a way to go, even for experimental projects with low chance of becoming a product?
Well, assuming that you have already this library or framework in place, we are applying it even for things that might substantially change, because swapping the clients and swapping the type of service is so cheap. And I already witnessed a swap from, or a POC of swapping MongoDB to Cassandra, which was scratched after a week of experimenting. And we were able to do this switch in really a week, including some deep search in the API documentation. Or we can apply it to services that we might shut down in a few weeks. I wouldn't recommend it for really the research, like the when you are trying to prepare the models and play with them. But they are really hidden in one small bit of what I presented. So that kind of research goes elsewhere. But once you put things into production, even like tentatively as an MVP, I wouldn't be worried about using such approach. But building this framework on your own for one experiment, it wouldn't pay off, of course.